Hi, my name is Panos Ioakim, and I'll be presenting the paper on demand MEMS accelerometer dynamic response acquisition and output dithering by self-test pin actuation, also on behalf of my colleague Iasonas Triantis. What this work entails is the use of the self-test pin present on the ADXL series MEMS accelerometers from analog devices. On the right-hand side here, a frequency strip stimulus on the self-test pin was used to actuate the mass internally electrostatically. We can see the output here, where the frequency response can be seen to undergo a dip, which is due to the internal filtering electronics of the chip itself, followed by a mechanical resonant peak before the overall response declines. It's been found that stimulating the self-test pin around about the 6 kHz region produces a small output which can be useful as a dithering to any mechanical input. Much more useful, however, would be if at any given time one could verify the impulse response of such a sensor, and applying a 20 microsecond impulse stimulus on the self-test pin provides such an impulse response, as we can see here. This impulse response then, by standard DSP theory, convolved with any input would give us the output of such a sensor or system. Being able to acquire the output as normal, but also the impulse response by deconvolution of the impulse response and the output, one, in theory, could derive the unchanged input stimulus. In order to show this a little bit better, we purposely band limited a MEMS accelerometer to 5 kHz, and we applied a 1.5 kHz sinusoid intentionally corrupted with a 7.5 kHz noise. Having gone through the convolution process with the impulse response of this system, we can see that indeed the output is in fact exactly as expected, i.e. the 1.5 kHz signal undistorted with a trace of the noise signal at 7.5 kHz. This shows that acquiring an impulse response using a self-test pin is indeed a way of being able to not only predict the output, but more importantly, being able to derive back to the original unaltered input by deconvolving the impulse response with the acquired output. Thank you for watching my presentation, and I'm looking forward to answering any of your questions.